So next, I'd like to introduce to you Dr. Detlev Helmig. He is a fellow and associate research professor at a very cool acronym INSTAR, Institute of Arctic and Alpine Research, at the University of Colorado at Boulder. His research is focused on atmospheric chemistry and transport, atmospheric measurement techniques, and surface-atmosphere interactions. Dr. Helmig has studied the presence and patterns of atmospheric hydrocarbons, volatile organic compounds, and ozone derived from oil and natural gas development along the Northern Front Range. Got it. Mouthful. Thank you. Let me introduce to you Dr. Detlev Helmig.
What I'm going to show here is in the works. It's partially preliminary, hasn't been published yet. And this was funded by Boulder County Public Health and Earthworks. Also, I'd like to acknowledge colleagues and good collaboration we've had with the Colorado Department of Public Health. They've been hosting us in the facility and been really good at sharing data and helping us understand the observations. And I have 4 points on my overview, but I think I've wasted too many slides, so I'll see how far I can get. And then I'll leave it there. So let's start out. I'm going to scare you with some real molecules, some real structures. This is what we're working with. So these are petroleum hydrocarbons. And these are the bulk, the big guys we see out there in oil and gas emissions primarily. And they can be broken up in two different source categories. The lighter molecules, so you see methane there. And then from there, the molecule keeps going through ethane, propane, butanes. So that's mostly the natural gas associated hydrocarbons. And then as they get heavier, they turn into fluids, eventually into oils. So those are listed on the right side. You can see there's aromatic compounds there, benzene, toluene, the BTEX compounds, and we've talked about those. So it's a wild mix. We see, all of that's out there, and depending on if it's more gas or more oil, you see more of one or the other. If it's a dry gas, you see mostly methane. If it's a wet gas, then you see more of the heavier constituents. So that's what we are looking at. And about the sources, we talk a lot about methane, and methane is a tricky one, because methane, yeah, it comes from oil and gas, but there are also quite a few other sources, and some of those here in the region, as you may have seen. So when you see methane, it's hard to tell, where's all that methane from? But we have something that's beautiful, it's beautiful, and that's ethane. Ethane, you see all the errors come from here because ethane is predominantly emitted by oil and gas operations. So it gives us a real good tracer compound. But I also show you nitrogen oxides because they play into this ozone question that we've already heard about, and I added this here. So when it comes to ozone, ozone is not emitted from any of these sources. So ozone is produced in the atmosphere. I have a sun here that shows this is a photochemical process, and what you need is these nitrogen oxides that can come from quite a few different sources as well, with oil and gas being one of the sources. And then you need, it's not just ethane anymore here, but all these VOCs. So that long list I showed you before, plus VOCs that can come from some of these other sources, all these mixed together in the atmosphere. That's how you get ozone. And we're going to touch that a little bit as well. So I talked about ethane being a beautiful tracer, way for us to tell, oh, is this oil and gas or is it something else? But we have something else. And that was just discovered the last 4 or 5 years. And we call that the I/N pentane ratio. It's basically the relative ratio of these two isomers of pentane. And it turns out that when you have oil and gas sources, this ratio is really close and steady, right around 0.9. So I put the fingerprint here, because that's the fingerprint of oil and gas emissions. Whereas when you have other diverse contributing sources to pentanes, this drifts all the way to the 2s, 2.5s. So looking at that ratio, we have a really nice second tool out there. We can tell, is this influenced by oil and gas or something else? So that's a study we're doing right now. It's at the Boulder Reservoir. The Boulder Reservoir is right here, and there's a CDPHE monitoring site right here at the southern tip. And what I want you to note is that it's a park. It's a city park. It's a recreational area, and it's mostly surrounded by farming, actually. It takes a couple, 3 miles before you get into the city of Boulder. Denver's down here, Fort Collins is all the way up there. And this is what we're monitoring at this time. So these are nitrogen oxides, methane, this list of volatile organic compounds. Then ozone is measured by CDPHE. And then what we think has really made a big difference in sharing that with the public is we have a public project website, and that reports these measurements in real time, live, in real time. You can go there right now and look at, hey, how much methane, how much ethane do we have at the Boulder Reservoir right at this moment? This is how the facility looks, not really all that fancy. A small shelter, air being pulled from these inlets and towers, with instrument being operated inside. Again, this is where the station sits. And to put this in perspective to the surroundings, so Denver is here, Longmont is here, Fort Collins somewhere up here. And these are all the oil and gas wells. We've seen this before, some 25,000 or so. You can see it pretty much all to the east, northeast, a few southeast, and then to the south is Denver, Golden, and so forth. So this is exactly where we are. So bear this in mind, because that factors in some of the data analysis. So we've been doing this since March 2017. It's running still as this time. We've done over 7,000 samples of VOCs. I think we hold the state record now with the most VOC analysis ever accomplished in the history of the state of Colorado. I'm pretty sure I'm right on that. Many, many measurements of methane, lots of NOx measurements. So since this is automated, it runs by itself. That's how we can get these very, very high numbers. The other amazing thing is this is at the bottom of that website I mentioned. That site has been visited more than 15,000 times by now, 15,000 times. There's people looking at this all the time. So start looking at some real data, a few examples. We call these time series graphs. So what they show, 3 days of data, so that time is here, concentrations are here, and this is cut off. Up here it says events, events, events. So what we see changes in these concentrations. They bounce up and down all the time. So we see these events. These are plumes coming through over the site. The concentrations go from a background, this is the background of methane, and they go up. They go about by maybe 10% here in methane. And at the same time, all these VOCs go up. This is ethane, propane, butane isomers, pentane isomers, hexane. What is this? Ethene, propane. This is benzene and toluene. So these come together. It's not we see one of these VOCs. They all come together. It's like the fingers of your hand. They all move together. You see one go up, the others go up. And the ratios are actually pretty consistent. And then if you need to look closely to read these concentration scales. So you see a 20 here, you see a 5 here. Numbers become smaller. So the increase in total concentration is the highest for ethane and propane. Butanes are all quite a bit less. It gets less and less. And you can see even the benzene and toluene goes up here, but this is a relatively small change in absolute concentration. Yeah? So the highest amount in terms of mass that we see in these air plumes is ethane and propane, and then you see a little bit of this, and there are more. I've only picked out a few. But they become smaller, the relative amounts, as the molecule becomes bigger. Again, that's the same event. I want to show you how this fingerprint works. So again, this is ethane and propane, how they went up. And right at that time, when this plume goes through, you see this ratio of the pentane isomers, boom, goes right down 0.9, and it bottoms out there. And then as concentrations drop again, it goes back up where we have a more diverse urban signature. So when we see these plumes come through, you have this very distinct oil and gas signature. This shows the wind speed and wind direction from the site. And what we see very consistently when these plumes come through, wind direction, these circles here, it drops, it goes right to easterly, northeasterly winds. Right here, this coincides with when this event came through. Okay. And then another thing that's very characteristic, so when we look at these plumes, what we can do is we look at, well, where did the air come from? So what you can do, you can go to NOAA database, and pull out these, they're called bag trajectories. So it shows you which path the air has taken before it got to the site right here. And what we see most times, it came somewhere from the east, right here over I-25, Weld County. Okay, so one more example, and this is actually a real interesting case. And that's so far out of 6,000, or what was the number, 7,000 measurements we have, it's the highest one. It's the event with the highest levels of VOCs that we ever observed, and it happened in December 2017. So again, ethane was actually really close to the background here, just a few single digits, parts per billion, and then woo, it went up to 120. So an increase by a factor of 100, just in a few hours. You know, just these points are spaced every 2 hours. So, well, when it's way back up, you can see with the same plume, benzene and toluene went up. The total increase was less. So it was to about 1 ppb here for these guys. This is 120 ppb. Yeah? So, but you can see how nicely they coincide. It all goes together again. The pentane ratio went way down to the 0.9. Winds again here, right from the northeast. And then what we did as well, we looked at the air path that coincided with these 3 data points. So this is where we are. If we go back in time, these numbers here show hours in bag transport, and they came kind of, you know, they're all this region, and there's increasing uncertainty the further back you try to analyze the path the air has taken. But then what made this really interesting is that this, you know, this air path coming over Longmont, Loveland, and it came over this location here, where on the same day there was a well site explosion, and that received quite a bit of attention and was in the paper, in the news. So near Windsor, this site exploded. But that was in the evening, which that seemed a little bit not to match. So this happened in the evening, but we actually saw this a little bit earlier on the same day, between 2 and 6 p.m. And then when you take this air path back, you know, it took about, you can see these numbers here, 6, 7, 8 hours for this transfer to happen. So that, you know, if we assume there's this association, since, as I said, that was the by far highest event we've seen, so it raised the question, did these emission leakage release results from this explosion and actually occur, you know, quite some hours prior before this explosion happened? The other question, of course, is if we saw 120 parts per billion of ethane here, parts per billion of benzene, you know, what were the concentrations on this path? Air, as it travels across the landscapes, it mixes, it dilutes. You know, it never really concentrates, it always dilutes. So we don't know, because there's no other site here where any of this monitoring is conducted, but it certainly was more, the concentrations were higher, and it's really uncertain what levels may have been along this trajectory path. Okay, so these were a few events, and what I'm going to do now is show you, you know, analysis of that whole data set. So how do these concentrations behave, relate to conditions we have in the atmosphere? So it's a very easy one. I guess most of you will relate to this. Wind speed. As winds go up, levels come down. Yeah? If you want to have clean air, go outside when it's windy. If you want to go on your walk, hike, take your dog, you know, that's when there's the cleanest air, when it's windy. You may not like it, but that's when the air is good. Calm conditions, still air, you know, levels are much higher. A very clear dependency. Seasonal behavior, and here again we take ethane. This is data binned by month, a full year. Goes April through the summer, winter, and back into the summer. You can see in the winter, these are distribution graphs where this is the mean, this is the median, this is the 25 percentile, the 75 percentile, and then extreme values are these crosses. You can see in the winter it gets quite a bit more, at least a factor of 2. And it's mostly driven by how our atmosphere mixes, how our atmosphere behaves, how strong inversions are, how long they last, because they trap the pollutants that are emitted nearby from nearby sources. They trap those right at the ground. So that's mostly reflected in this behavior here. So higher concentrations in the winter. So if somebody wants to assess your air quality, be sure to measure in the winter, not just in the summer. It's at least a factor of 2 in there. Diurnal behavior, ethane and benzene here. This is from midnight to midnight. At the night, levels build up. During the day, they actually come down, almost a factor of 2 for ethane. So early afternoon, compare this with here, early morning, it's about a factor of 2. Then they build up again. Benzene, similarly. If you compare this with traffic counts here, that's diurnal traffic on Highway 36. It's just the opposite. So you would think, you see all these cars there. You see these traffic jams, cars everywhere. No, actually, atmospheric levels for these compounds are lower during the day because the mixing you get during the day from all the convection is actually a stronger effect, at least for these compounds, than the increase in emissions. And we see that for many of the compounds that have a more diverse mix of sources. So again, it's higher at night. So add that to the seasonal component. So you compare winter nights with summer day data, there's a factor of 4, something like that in there, just from these seasonal and diurnal dependencies that are all driven by mixing. This has nothing to do with diurnal changes in emissions. It's just all driven by how the atmosphere mixes. So then what we did here, well, so how do the data from the Boulder Reservoir compare the scale with other locations? So here we have the concentration here. We have, there's 2 graphs, and it starts on the left. And that compares the Boulder reservoirs right here. Again, it compares the distribution where the median is here, the mean is here, extreme values are here. So what we had for that 2017, I think, we had like a mean ethane of 5 point something parts per billion. And this is the most detailed study I could find in the literature. It compares measurements from 28 cities in the United States. So what was seen in those? And this goes back to 1999 to 2004. So what we see at the Boulder Reservoir is actually really hard. You can see there's only 2 other places, Pittsburgh, Charleston, that had higher ethane. And all these other cities were significantly below what we see at the reservoir for ethane. Now, this is almost 20 years ago. If you apply trends we've seen in urban areas, I use the trends seen from LA, where most of these VOCs have come down actually over the years. The cities have really cleaned up the last 20 years for VOCs. If we apply those trends, then actually what we see at the Boulder Reservoir right now is higher than these reported values in any of these other cities. So even though this is not even in an inner city at the Boulder Reservoir, what we see for these petroleum hydrocarbons at the Boulder Reservoir is really high. It's high with, compared to all these other sites included in this studies and other places out there. You can compare that with. So there's now a different analysis I want to introduce you to. So again, a map showing the site right here. These are the wells. Again, all these dots are well sites. So we're sitting right here, and this shows the wind directions. The wind directions, and this is from all data, February to September, a year and a half of data. It uses CDPHA wind data, and this is filtered for relatively high wind speeds because when you filter at low wind speeds, the air flow really isn't that well defined, and you suffer from local effects and topography and trees and things that are nearby. So to get a clearer signature, we took the stronger winds, the moderate winds and stronger, anything above 3 meters per second, and just focused on those data. So the size of these pies shows you how frequently the wind blows from a given direction. So at the Boulder Reservoir, we get a lot of winds right from the west, we get a lot of winds from the northeast. It's just really 2 predominant wind directions out there, at least for these heavy winds. And then we put on top of that the concentrations we see in ethane. And you can see there's really a clear signal that when wind blows from these sectors here, you have much more reds, much more higher ethane, whereas when wind comes from the southern direction over the city of Boulder and from Denver, it's relatively less of the red, so lower concentrations overall. So this is ethane. We're quite surprised that we saw something very similar for benzene, with all the urban sources here, the Boulder being right here, Denver right here. Winds don't come from there all that much, but still the highest levels we see in air transported from these northeast sectors. So that's benzene. Now this is the fingerprint, remember, the pentane ratio. And here, when the ratio is high, so the red colors, it means it's a mixed source, it's urban, it's traffic. So in this case, what we get for the hot colors is transferred from the mountains. It's non-oil and gas, whereas when air gets transferred from here, and it makes a lot of sense, you get the lower values. I remember 0.9 was about where it bottoms out. So you can clearly see that air coming from here is dominated by this oil and gas signature. So now what we do, we take our 8,000 measurements we have, and we do this back trajectory every time for every single point, and we let a computer program and process all these data. And this is called potential source contribution function analysis. So we do this over and over and over, and from that we can get this footprint analysis. So we're sitting here right at the Boulder Reservoir. So what's the likelihood to get elevated ethane? And that means when ethane is above, the median, when air is traveled over any of these pixels here. And you can see that, when we get high ethane air originating in these red areas here, whereas when air comes from the mountains from the west, ethane is much lower. So the hot spots are right here to the northeast again. So this is for ethane. For total VOCs, we see something very similar. Total VOCs are of interest because of the ozone question. Again, so this is total VOCs. Now, this is the pentane ratio again. And here, the hot colors are actually south of the reservoir. So here's the city of Boulder, and you can see the transportation sector, the turnpike into Denver, because, the high values here are from traffic, whereas the low values, this is the oil and gas signature. This is for nitrogen oxides, the same analysis. And here's, it's pretty high here is where all the cars are. There's some nitrogen oxides. But also this whole basin here seems to have a pretty significant NOx contribution. Okay, to show you again how the ethane footprint aligns with the oil and gas well distribution. So you can still clearly see there's a pretty nice overlap, high ethane footprint with where the oil and gas well locations are the most dense. Okay, then something else we did, trying to learn. So how much is emitted? So what are the total fluxes? And what we did is we focused on these events, these peaks, where we're pretty confident that this is a clear oil and gas plume that's going over the sides. And we filter out those data. We look at the relationships between ethane and methane. And it's pretty well defined and actually compares quite well with other published data from the region. And I don't have enough time to explain this step by step. So let me summarize what we find. So then scaling that ratio to published basin-wide flux data from methane, we get an ethane flux for the region, and this is per year, of 36,000 tons. We have a way to scale this to total VOCs. That gives us 134,000 tons. Then if you add the methane plus the ethane, the other VOCs together, you get something like 292,000 tons, or it's the same as 292 gigagrams. If you compare that with how much gas is being used by your household, so this roughly corresponds to the annual use of 146,000 households, which is actually more than Boulder County has. Another way to do this, I converted this into tons per year, which you can convert into barrels of oil. So this fills about the biggest super tanker you have right now in the ocean out there. So they hold about 4 million barrels of oil. So all the VOCs and that end up in the atmosphere from the region, it's about equivalent to what you could fit in one of these tankers. You can put a value on that at $50 a barrel. You know, that's about the value of that lost oil and gas. Nothing you can do, you can compare it with how much you get from automobiles. If you scale it to that VOCs, they account about 10 to 15 times roughly, you know, give it a factor of 2 or something, but just to give you a scale, 10 to 15 times the VOCs that are emitted from all automobiles per year in Colorado. Okay, I'm doing the same thing for benzene. We estimate something like 620 tons per year. So that's about 22 of these tankers filled with liquid benzene. Okay, I think I have a few more minutes because I thought it was 30. So let's go to one other topic, and this is ozone. And as I already said, that ozone is a secondary pollutant, so it's built in the atmosphere from nitrogen oxides and VOCs. So we're concerned about ozone because it poses a very strong respiratory stress and risks. You know, these are impacts from elevated ozone. Also, there are studies that show, you know, just across the United States, there's, you know, quite a notable number of people who suffer from that to the degree that it causes premature death every year. So let's look at the ozone from the side, and these are data from this year, July 2018. So this is 30 days of data of ozone from the Boulder Reservoir. This red line is the air quality standard, the way it's defined in the United States right now. Bear in mind, this is a compromise value. It's not necessarily means it's safe or it's dangerous when you are above. It's a compromised value, and you know, compare it with the standards in other countries, you can see that the EU, Japan, Canada, they have ozone standards that are quite a bit lower. What you see clearly is that with the current standard during the summer, we were above this standard many, many times. You know, this is the 1 hour mean, the 8 hour mean, and the 8 hour mean is the one that applies for regulatory purposes. So taking the whole year, last year, all together, we actually saw the highest ozone value in the Front Range at the Boulder Reservoir. We had a stretch of 5 days where we exceeded the standard. I already said it was the highest ozone value in the last 10 years for Boulder. We had 230 hours where ozone was above the standard. 100 hours where the 8 hour ozone exceeded the current standard, and that accounted to 32 days where the ozone standard was exceeded at the Boulder Reservoir. To show you how we compare within the nation, this map shows current non-attainment areas in the United States, non-attainment for ozone. And so you can see this is the Northern Colorado Front Range. You know, about maybe 7–8% of the United States is non-attainment of ozone. The worst areas, the California Central Valley. It looks like we're going to be bumped up from a moderate to a serious non-attainment area here. The colors give you the severity of the attainment. And this shows the trends in ozone over 2000 to 2014, paper that was just published. Arrows pointing down, meaning ozone has actually gotten lower, so ozone has gotten better over this time period. You can see lots of down pointing arrows. The colors give you the degree of significance. We can see clearly that here the Front Range deviates from most other regions in the United States. We're really sticking out in terms of, you know, how has ozone changed? Ozone has not improved in this region to the degrees has improved in many, many other regions across the United States. So then we did the same analysis I showed for the VOCs with this footprint analysis. So we take, you know, the ozone data from the reservoir, look at, oh, this is cut off. When was ozone, where did ozone come from when it was really high? This was the footprint of the high ozone transport. And this, and again you can't see it, this is just for the days where the standard was exceeded at the Boulder Reservoir. And you can see we never get ozone exceedances with air transport from Boulder or Denver or Golden, or even Fort Collins for the Boulder Reservoir. All of our exceedance days are tied to air transport from this area here. And again, this gives you a comparison to put this to scale where how this aligns with the distribution of oil and gas. Okay, and I think I'm about done with my time window. I want to touch a few more things on how this scales to health effects. So I'm just going to scroll through this right now. The one point I wanted to make on this, I'm not the expert on health effects, but when it comes to air pollutants from oil and gas, bear in mind that it's a matter of scales. It's a matter of scales because the pollutants that are of high concern in close proximity at the site, these are primary emissions, they are fracking fluids. They're different than when it comes to the regional scale. To the regional scale, ozone particulates are really high concern. Then also think about the global scale, because here ozone is again a player, but VOCs, CO2, and methane play a significant role, and all that factors into how do we assess, evaluate the impacts from atmospheric emissions from oil and gas operations. Just a summary of what I had here, and I'll leave this up while there may be some questions. So thank you. Okay. Oh, just nice questions. So there's some questions related to this transport effect. There's some questions related to even isotopic signatures to evaluate the origin of atmospheric methane. It's a really good one, and it's a whole line of research by itself. So it's methane, the carbon comes in different isotopes, stable isotopes, carbon-12, carbon-13, and it has different signatures depending on the time of source. It's been used for a measurement tool, but it's complicated, expensive, and it's not anywhere close to as simple and cheap as the ethane monitoring or the pentane monitoring. So in the last 4 or 5 years, there really has been a shift in this research and a nice development of new tools. We understand now much better how to pinpoint, how much of these elevated levels we see come from one source or another. So it's a good question, but it hasn't been used in this context a whole lot. Then this is a good one. What are the implications of your research, policy, development? Who is using it? For what purpose? So the motivation of this study, as I said, it was funded by Boulder County Public Health because the moratorium that Boulder County had ran out a year plus ago, and Boulder County was concerned about air quality impact of this potential development of oil and gas operations within the county. So that's how and why they contracted us to set up the site and actually originally it was just 1 year of this monitoring to establish a baseline. So how do you know air has become more polluted and how certain compounds have changed versus others because of a change in the industry, growth in operation and so forth? You need a baseline, and we really don't have these baselines for most situations. So Boulder County was thinking about that. They asked us if we could do this. The facility was already there, so that was easy. So we just put some instruments in there, started monitoring for a year. And then the question came up, so we want to know in 5 years with maybe so many new sites, well sites, how much of a change was there? And that's really, really hard. When you do this type of research, you need to consider that the atmosphere is highly variable. It's sunny, it rains, it's windy. It's not. And so you can see with these events, if you measure on one day, you may get 2 parts per billion. You measure another day in the afternoon, you may get 20 parts per billion. And it may just be within 2 days. So what you see this high variability. So to tell with certainty from 1 year or 1 day to another year, another day, that there has been a change in emission, it's almost impossible. You need a real good, solid data set. It needs to be of high quality. I'm a firm believer that these continuous measurements are of much, much higher value and have much higher potential to derive those answers. And based on that and a lot of public feedback, I showed you these 15,000 visits over the year, a lot of public feedback we've received over the last year. Boulder County has now decided to support this through another year. So it's up and running. You can go online, you can look up the data. So that will give us a 2.5 years record as of right now, and I hope we can keep it up and running. As far as I know, it's the only ongoing real-time monitoring of these petroleum hydrocarbons in the state at this point. Continuous high-time resolution monitoring.
Thank you. I really appreciate it.